we're going to go over how to do trig form of complex numbers. So it's a lot like you guys were working with, about a couple weeks ago with vectors, where we have to have our magnitude and our direction. Same thing can be applied for complex numbers. So this is very similar to the stuff that we worked with vectors. We're just going to be writing it in a slightly different format. But otherwise, the math behind it is all very similar to what you guys did a couple of weeks ago. So to go over some of that stuff, here we've got, complex numbers. We can actually graph complex numbers. They're just on a different plane. We would graph them very much like we would graph vectors, or like we would graph almost just coordinates anyway as well. So for example here, the complex number 3 plus 2i. This is one number. It has a real portion and the imaginary portion, or the I portion, but it is one spot, is one location, is one number. So to get that spot here, I'm just going to put this red dot. I'd say we'd go over 3 and then up 2, right? 3 on the real axis, 2 on the, it's called the imaginary axis, right? And that's where that point, or where that number is located. Where the number -4 plus 5i is located, we'd back up 1, 2, 3, 4, and then we go up 5. There's -4 plus 5i. That's where that one is. And then same thing here. 2 minus 3i would be located down in this area, right? That's where that one would be. And you can do that without any I values as well. If you wanted to just graph the point -3, that would be back 1, 2, 3, and it'd be right on the axis right here. Or if you wanted to graph the point 5i without the -4 on there, that would just be right here at 5i, right? So you can graph any complex number, can be found on what's called the complex plane, right? But it's the same as graphing a point. Basically the same thing, we just call it something slightly different because we're working with a little bit of different math. But otherwise, essentially, it's the same, right? And we can go here with absolute values. We can find absolute values of complex numbers. Absolute value really just means how far away are you from 0. And so it's very similar, or pretty much the same, as finding the magnitude of a vector, right? That's the same thing. So here, if I wanted to find the absolute value of 3 plus 2i, that's right here. What I would do for that is, this is up and down 2, and this way 3, right? You can kind of pull it off these two numbers too. If you look up a formula for it, it'll say, oh, do the square root of a squared plus b squared. Well, really, that's just the Pythagorean theorem. That's all it is. It's just there's a little triangle right here, 2 up and down, 3 left and right. So we take 3 squared plus 2 squared. I mean, that's what that would be. It'd be the square root. Oops, let's put that in there. Square root of 3 squared plus 2 squared. And that's all we have there, right? Which, this one doesn't work out, or work out perfectly. It's, the square root of 13. That's what this one is here. So I get that that's going to format. I'll maybe put that a little bit lower there so we can see that. But that's where that one's going to be. And the same thing with the rest of them. If I want to find the 4 by 5, that'd be 4 squared plus 5 squared. Technically, it'd be -4 squared, but taking -4 times -4 is the same as taking 4 times 4, right? We'll still get 16 in there. And in that case, we do 16 plus 25, which would be square root of, 16 plus 20, yeah, 16 plus 25, excuse me, brain shot. Brain went out for a little bit. But in there, we just say, yep, that would be the square root of 41, and you can leave it in square root forms. Same thing with this last one. This purple line should actually have the same length as this red line because it won't matter what order they're in. We could actually just take this and say, yep, it's the exact same work down here, because you're still going to take 3 squared, you're still going to take 2 squared and add those together. It's not going to make a difference. So that part's not too bad, but that's the hypotenuse, or the absolute value, or sometimes called the radius, because that's kind of like going around a circle. So at times the absolute value can also be called the radius of a number as well. So a little bit of an aside before we get really into the trig form stuff, just to kind of remind ourselves, essentially what we're doing, we're setting up this right triangle, and we've got, our angle, we've got our radius, or our absolute value in this case, and then we've got our vertical stuff, our y value and our x value, right? And we can do sines and cosines. We can also do tangent, right? I guess I didn't type that one in here, but sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. We can put those in. And so now we can kind of update that a little bit with complex numbers. And I get it's like, oh, you just changed the letters around. But that's because usually with complex numbers, the first number is an a plus bi, right? That's what we did here. A plus bi. So a is usually horizontal, b is vertical, right? When we're talking with complex numbers, a little bit different there. But otherwise, the formulas are still the same. So we could take this formula and multiply the r over, say it's b equal r sine. Here we could say this is a equal to r cosine, right? And so in here, I know there's a lot of stuff on here. I'm going to walk through those one at a time. So maybe let's do one of these, and we'll hide that so people don't freak out. So in here, we have this portion, and now what that allows us to say is a is r times cosine. So I'm just going to replace a with r times cosine. And b is r times sine, so we take b and replace that with r and sine. And I put the I in a little bit different spot. It's the same thing, right? It's all multiplying, so we just put that there, right? B times I, r sine theta I, right? It's all right there. And then we can kind of rearrange it. This here, right here, this is called the trig form of a complex number. We have, instead of doing left to right and up and down, we have the absolute value or the magnitude and direction. Same as a vector, right? We can have that be either way. And so there you can rearrange some of the stuff a little bit. Here I just factored out the r. And just to abbreviate some of that, here this is cosine of an angle plus I times sine of the same angle. They'll be the same angle in both spots. So a way to abbreviate that, since it's cosine of angle plus I times sine of angle, is what's called the cis form, right? It sounds weird to say that, but that's exactly what that's called. The cosine I sine of theta. So you can abbreviate that a little bit so you don't have to write out cosine of this plus I sine of the same thing, and you're not repeating yourself. This is just an abbreviated form of that. Otherwise, it's all the same thing. So to show you a couple examples on how we could put things in trig form, this one, 5 minus 12i, I went ahead and just kind of made a quick sketch of that. Over 5, down 12, so I know where it's at. The r value, that wouldn't be too bad. That would just be the square root of 5 squared plus 12 squared, right? Let's see if I can type that all in here. Plus 12 squared, right? Which, when we work that all out, you can grab your calculator, you can type that in. I've done that a little bit ahead of time. The square root of 169 will end up being 13 there. Now to get the angle in here, you can use the hypotenuse, you can use inverse sine, inverse cosine. I like to use inverse tangent just because I automatically know these two numbers, and just in case this doesn't work out nice, I don't have to worry about square roots. This opposite side is 12, the adjacent side is 5. So we could do here the inverse tangent of 12 over 5, right? And if I type that in my calculator here, let's make this a little longer. Let's see, the inverse tangent of 12 over 5, we get 67.38. It's always good to go about 2 decimal places out there. That's always a good idea on there. We don't need shortcuts. Yep, we just need those. So 67.38 degrees, but that's not the full story. Again, 67 is just the direct, just this reference angle in there. So the actual angle, so maybe I should change this and say this is the reference angle. The actual angle will be, you can put this in a couple of different ways. We can either say it's the negative version of this angle, since we're, going backwards a little bit, or possibly, now let's go down here. Or we could say we could take 360 minus that value, because we could do that. So which is 292.61. 292.61. So how we would put that into trig form, there's a couple of different ways that we can do that. We can either type it in the long form, which if you want, long form would be 13 times cosine of the angle, which is 292.61 degrees, plus I times the sine of the angle, which is 292.61. And I forgot to put the, there we go. Got to put that in there too, right? So this is the long form. That's okay as well, right? I mean, this is one form. I usually don't write it in this form because it's long and it's clunky and it's tough to do that. The short form of that is to say, okay, well, we can put it in 13 cosine I sine of, well, 292.61, right? So it's a little bit easier sometimes to write it in this cis form. They mean exactly the same thing. It's perfectly fine. Doesn't make a difference. That's okay there, right? So that's how you get the R value and the angle, right? You know, if you want to jump ahead to the next example, you certainly can. Here, I'm just going to show this one. It's back 8, up 15, same type of thing. Here, I would take the R value is equal to 8 squared plus 15 squared, and then take the square root of that, which ends up being 17, right? That's what we would have there. And the angle, I'm just going to abbreviate that, would be, again, the arctangent of 15 over 8, because, again, this side's 15 and this side is 8, so we'd have opposite over adjacent. We could type that in our calculator, double checking on that. 15 over 8 is 61.93. And then I have to make my adjustment to find my actual angle, which would be 180 minus whatever that angle is, right? So I would do that and say, oh, that's about 118.07 in that case. And so the trig form of this, I'm not going to write it out in long form because I don't want to take all that time. I know the radius is 17 because we figured that out by doing the square roots. And then this is 118.07, right? I'm just going to put it in that abbreviated form. That's where we put that stuff. Okay? That's putting something into trig form. We can do that. It's that cis form there. And now, why would we use trig form to do this stuff? That I'll share out here. So why we would use trig form, okay, is because some things are easier in Cartesian form. That's in this a plus bi. Some things are easier in trig form. So adding is way easier to do in Cartesian form. This super easy to do in Cartesian form. We just add, 5 and -8, we get -3. These two together make positive 3i. So, I mean, we can do that very quickly. It's -3 plus 3i. We can add things together very quickly in Cartesian form. It's, not that difficult to do. But multiplying things in Cartesian form takes a little while, right? We've got to multiply this stuff out. And I'm actually going to work this the whole way out. If you want to skip ahead, but I'm going to work it out because we'll see that it's the same thing the other way. So here, when we multiply this, -3 times, whoops, that's not what we wanted. We wanted this to be a 5. Well, you guys can jump ahead here while I fix this version on this one, just so I don't have to type the whole thing in there. All right, let's see. We want it to be a 5 minus 12i. That's what we want. So let's take that out. Okay. So in here, when we multiply that stuff through, 5 times 8 being -40, and then I suppose we'd also have, all the little pieces on here. Let's see, we'd have -12 times 15, so 180 I squared. That's from these two. And then we'd have positive 12 times 8, which is 96i. And then we'd also have our 5 times 15, which is 75i. And boy, then we got to work that stuff out. Well, we can just insert that right in there. All right, now we got to work all those portions through. -40 plus 180. Oops. negative 40, which will be 140, because again, the I squared is negative 1, and then plus, oof, 96 plus 75. I'm just going to use my calculator. 171I. Woo-wee. All right. So do all of that work and we can get down here. It takes a little while. It's not impossible, but it is a little bit harder, right? It is a little more difficult. It is, in fact, a lot easier to do in Cartesian, or sorry, in trig form here. And I've got to back up a little bit because I am realizing that I put the wrong typed the wrong number in here, so I've got to fix that just a little bit. Let's see if we'll pull that in, because it's not, you know, we're not this number here. We need this to be our actual number, which is 292.61. Yeah, it's 292.61. That's what we have there. That was our old one. So if we change those and use these ones, it's actually a lot easier to do the trig form in this case. All we do to get this trig form in here, okay, is we take the two outer values and we just multiply them, right? I can take 17 times 13, right? And that's 200, oh, now let me get rid of this. Okay, that's 221. That's 13 times 17. And then what we do with the two angles, when we're multiplying two things together, what actually happens to the angles is they end up adding together. It's sort of like a rotation in a sense. So actually we could just take 292.61 and add it to 118.07. And that's 410.68, right? I mean, that's what we have there. It's that many degrees when all said and done on that. Now this is bigger than 360. So again, we could say, well, we went all the way around the circle and then a little bit more. So we could remove 360 from that and really say, oh, this is actually just 50.68 in that case there. So that is a heck of a lot faster. And now we are essentially done. But I know some of you guys are probably thinking, this sure doesn't look the same as this one when we multiplied it, does it? Well, here's what we would do. Because this is cosine I sine. Again, cosine is giving us the A value, the left to right. Sine's giving us the vertical value, up and down the I value. So what we can do is you can just jump right to your calculator, and I can type in 221 times cosine of 50.68, right? And we can type in 221 times sine of that, right? So let's go here. So I'm just going to put that in the calculator. 221 times cosine of 50.68, right? And 221 times sine of 50.68. And what we get is pretty much the same thing. I mean, yeah, rounding errors are off a little bit in there, but it's still 140 plus 171i, which is exactly the same as what we found in here, right? It's exactly the same thing. Sorry, I just realized that you guys weren't able to see the computer screen. It's exactly the same thing as we find when we actually multiply them out. It just makes it a little bit easier. So we can just multiply those things, right? So that's a lot easier to do in trig form. Multiply the two R values, add up the angles, right? That's all we have to do there. Lastly, again, everybody's like, oh man, there's more. It's actually super easy. Okay, division, very similar here. Again, I typed the wrong thing in here, but I'll update that there. I'm not going to take more time with this video, but division is similar. Here, we would take this and just when we're dividing, we would divide the two numbers and subtract top angle minus bottom angle, and that will give you the angle. You don't have to go through using conjugates, things like that. You just divide these two numbers, subtract these two, and there you go. You have it in trig form, and it's all done very, very quickly. And I'll put that up here too, so you guys will be able to see that in the notes when you jump down through there. But if you guys have any questions on your assignment, send me an email and let me know.